Learning objectives. We will discuss the following topics in this chapter. Introduction and characteristics of weak methods. Heuristic search techniques. Generate and test. Hill climbing. Branch and bound technique. Best first search and A-star algorithm. Problem reduction and or graphs. AO-star algorithm. Constraint satisfaction problems. Means ends analysis. Introduction and characteristics of weak methods. What is weak AI? Non-sentient computer intelligence eventually focuses on a narrow task. Weak AI refers to the use of software to study or accomplish specific problem-solving or reasoning tasks that do not encompass the full range of human cognitive abilities. Example: a chess program such as Deep Blue. Weak AI does not achieve self-awareness. It demonstrates wide range of human-level cognitive abilities. It is merely an intelligent, a specific problem solver. Characteristics of weak methods. Self-awareness is not the focus of weak AI. It demonstrates wide range of human-level cognitive abilities. It is merely an intelligent, a specific problem solver. AO-star algorithm. Let graph G consist initially the start node. Call it init. Compute h of init until init is solved or h of init is greater than threshold or un_solve. Traverse the graph starting from init and follow the current best path. Accumulate the set of nodes that are on the path which have not yet been expanded or labeled as solved. Select one of these unexpanded nodes. Call it node and expand it. Generate the successors of node. If there are none, then assign threshold as the value of this node, else for each successor that is also not ancestor of node, do the following. Add successor to the graph G and compute h for each. If h of successor is equal to 0, then it is a solution node and label it as solved. Propagate the newly discovered information up the graph as follows. Initialize S with node until S is empty. Select S a node such that the selected node has no ancestor in G, occurring S/** to avoid cycle */. Call it current and remove it from S. Compute the cost of each arcs emerging from current. Cost of AND arc is equal to h of each of the nodes at the end of the arc plus cost of arc itself. Assign the minimum of the cost as new h value of current. Make the best path out of current with minimum cost. Mark current node as solved if all the nodes connected to it through the new marked arc have been labeled solved. If current has been marked as solved or if the cost of current has been recently changed, new status must be propagated to back up the graph. All of the ancestors of current must be incorporated in S. AO-star algorithm example is given here. Explanation. Nodes are numbered according to the order of their generation. Now, node 10 is expanded at the next step and one of its successors is node 5. This new path to 5 is no longer than the previous path to 5 going through 3. But since the path through 3 will only lead to a solution, as there is no solution to 4, so the path leads through 10 is better. AO star may fail to take into account an interaction between sub-goals. Assume that both C and E ultimately lead to a solution. According to AO star algorithm, both C and D must be solved to solve A. Algorithm considers the solution of D as a completely separate process from the solution of C, as no interaction takes place between these two sub-goals. Looking just as the alternative from D, the path from node E is the best path, but it turns out that C is must anyways, so it is better also to use it to satisfy D. In order to solve D, the path from node E is the best path which will tend to solve E. Since AO star algorithm does not consider such interactions, it will find a non-optimal path. Best first search and A star algorithm. Best first search. Best first search is a graph-based search algorithm. Detcher and Pearl, 1985. Intended to mean that search space can be represented as a series of nodes connected by paths. Algorithm defines a list. Open, consisting a single node only. The start node, yes. If the list is empty, return fails. Remove from the list the node N with the best score, the node where F is the minimum, and move it to a list closed. Expand node N. Return success and the solution by tracing the path from the goal node to S, if any successor to N is the goal node. For each successor node, apply the evaluation function F to the node. If the node has not been in either list, add it to open. Looping structure by sending the algorithm back to the second step. You can loop structure. Best first search, an algorithm in which a node is selected for expansion based on evaluation function f of n. Traditionally, the node with the lowest evaluation function is selected. Not an accurate name is given. Expanding the best node first would be a straight approach to the goal. Choose the node that appears to be the best. There is a whole family of best first search algorithms, but with different evaluative functions. Each has a heuristic function h of n. H of n is equal to estimated cost of the cheapest path from node n to a goal node. Example: in route planning, the estimate of the cost of the cheapest path might be the straight line distance between two cities. G of n is equal to cost from the initial state to the current state n. H of n is equal to estimated cost of the cheapest path from node n to a goal node. F of n is equal to evaluation function to select a node for expansion, usually the lowest cost node. Greedy best first search attempts to expand closest node of the goal, assuming it will lead to a solution quickly. F of n is equal to h of n, aka greedy search. Implementation: expand the most desirable node into the fringe queue. Sort the queue in decreasing order of desirability. Example: consider the straight line distance heuristic HSLD. Expand the node that appears to be the closest to the hold. Note: don't compare this with original map. This is not exactly correct distance. Just consider the given distance to understand this example. Heuristic straight line distance in of Agra is equal to 336. Notice that the values of heuristic straight line distance cannot be computed from the problem itself. It takes some experience to know that heuristic straight line distance is correlated with actual road distances. Greedy best first search example is given here. Complete. No GBFS can get stuck in loops. Example, bouncing back and forth between cities. Time. O of b to the power m, but a good heuristic can have dramatic improvement. Space. O of b to the power m keeps all the nodes in memory. Optimal? No. So that we are going for A star algorithm. A star algorithm. The A star algorithm uses a modified evaluation function and a best first search. The total path cost is minimized by A star. Under the right conditions, the cheapest cost solution in the optimal time is offered by A star. Evaluation function. The evaluation function f is an estimate of the value of a node n given by f of n is equal to g of n plus h of n. G of n is the cost to get from the start state to the state n. H of n is the estimated cost to get from the state n to the goal state, the heuristic. When the h of n is equal to actual cost to goal, only nodes in the correct path are expanded. Optimal solution is found. When h of n is lesser than actual cost to goal, additional nodes are expanded. Optimal solution is found when h of n is greater than actual cost to goal. Optimal solution can be overlooked. A star is optimal if it uses an admissible heuristic. H of n lesser than or equal to h star n, the true cost of node from n. If h of n never overestimates the cost to reach the goal. Example, heuristic straight line distance never overestimates the actual road distance. Algorithm. Create a priority queue of search nodes, initially the start state. Here, function f determines priority. While in the queue, neither the empty nor the goal found. Get best state n from the queue, if n is not goal state. General all possible children of n and save path information with each node. Apply f to each node and add to queue. Remove duplicates from queue using f to pick the best. A star algorithm example is given here. A star algorithm example is shown here. A star algorithm example is shown here. A star expands nodes in increasing f value. Gradually adds f contours of nodes like breadth first search adding layers. Contour I has all nodes. F is equal to fi, where fi is lesser than fi plus 1. Complete? Yes, unless there are infinitely many nodes with f lesser than or equal to f of g. Time. Exponential in relative error of h into length of solution. The better the heuristic, the better the time. Best case h is perfect, O of d. Worst case h is equal to 0. O of b to the power d, same as BFS. Space. Keeps all nodes in memory and save in the case of repetition. This is order of b to the power d or worse. A star usually runs out of space before it runs out of time. Optimal. Yes, cannot expand fi plus 1 unless fi is finished. A* algorithm. Applications. Pathing or routing problems. Resource planning problems. Robo motion planning. Language analysis. Machine translation. Speech recognition. Branch and bound technique. As a tree, branch and bound algorithms involves modeling the solution space. In turn, tree explores the most promising subtrees first. Exploration continues until either there are no subtrees left to break the problem, or we have arrived at a point where if we continue, only inferior solutions will be found. For each of the subclasses of solutions, one computes an upper bound to the maximum value of the objective function attained by solutions belonging to the subclass. Based on these upper bounds, a next stage of branching is carried out. New upper bounds are computed repeatedly until ultimately a feasible solution is obtained which has a value of the objective function greater than the upper bounds of all the subclasses and also higher than the values of the objective function for all previously obtained solutions. Algorithm. Search T, R, best. Tree. T is equal to solution space tree. R. Vertex in T. Best solution found so far. Post. Best equal to best solution found after searching subtree rooted at R. If R is a complete solution more optimum than best, then set best is equal to R. Generate the children of R. Compute bounds of vertices in subsets of children V1, up to Vk is equal to feasible children with good lower bounds for I is equal to 1 to k. If Vi has a promising upper bound, then search of T, Vi, best.
Example. Knapsack problem. Problem definition. Input. Weight of n items. W1, W2 up to Wn. Cost of n items. C1, C2 up to Cn. Knapsack limit S. Output. Selection for knapsack. X1, X2 up to Xn, where Xi
belongs to
0, 1. Sample input. Wi is equal to 1, 1, 2, 4, 12. Ci is equal to 1, 2, 2, 10, 4. S is equal to 15. Input. Weight of n items W1, W2, up to Wn. Knapsack limit yes. Output selection for knapsack X1, X2 up to Xn, where Xi
belongs to
0, 1. Sample input. Wi is equal to 2, 3, 5, 7, 11. S is equal to 15.
Branch and bound technique example is given here. Knapsack problem is shown here. Constraint satisfaction problem. Many real problems in AI can be modeled as constraint satisfaction problems and are solved through search. Example of constraints. The sum of three angles of a triangle is 180 degrees. The sum of the currents flowing into a node must equal 0. Constraint is a logical relation among variables. The relation is still maintained among the variables even though the constraints relate objects does not precisely specifying their positions and moving any one. Example, circle is inside the square. Constraint satisfaction. The constraint satisfaction is a process of finding a solution to a set of constraints. The constraints articulate allowed values for variables. Finding solution is evaluation of these variables that satisfies all constraints. What is constraint satisfaction problem? CSP. Finite set of variables v1, v2 up to vn. Non-empty domain of possible values for each variable dv1, dv2, up to dvn. Finite set of constraints c1, c2, up to cm. Each constraint ci limits the values that variables can take. Example, v1 is not equal to v2. A state is defined as an assignment of values to some or all variables. Consistent assignment. Assignment does not violate the constraints. CSP benefits. Standard representation pattern. Generic goal and successor functions. Generic heuristics. No domain-specific expertise. Once every variable is mentioned, an assignment becomes a completed one. A solution to a CSP is a complete assignment that satisfies all constraints. Some CSPs require a solution that maximizes an objective function. Example, variables v1, v2, v3 with domains d1, d2, d3. Constraints, set of allowed value pairs red, blue, green, blue, green, red. v1 not equal to v2. Solution, assign values to variables that satisfy all constraints. v1 is equal to red, v2 is equal to blue, v3 is equal to green. Properties of constraint satisfaction problem, CSP. Constraints may specify partial information. Values of its variables are necessarily being specified by the constraint. Constraints are non-directional. Typically, a constraint on two variables, v1, v2, can be used to infer a constraint on v1, given a constraint on v2, vice versa. Constraints are declarative. In order to enforce relationship, they specify what relationship must hold without specifying a computational procedure. Constraints are additive. The order of imposition of constraints does not matter. All that matters at the end is that the conjunction of constraints is in effect. Constraints are rarely independent. Typically, constraints in the constraint store share variables. Constraint satisfaction problem. Applications. Scheduling the time of observations on the Hubble Space Telescope. Airline schedules. Cryptography. Computer vision. Image interpretation. Scheduling your MS or PhD thesis exams. CSP example. Map coloring. Variables. Gujarat, Rajasthan, Punjab, Haryana, UP, Uttar Pradesh, Madhya Pradesh, Odisha. Domains. DI is equal to red, green, blue. Constraints. Adjacent regions must have different colors. Example, Gujarat is not equal to Rajasthan. Solutions are assignments satisfying all constraints. Example: Gujarat is equal to red, Rajasthan is equal to green, Punjab is equal to red, Haryana is equal to green, UP is equal to red, Madhya Pradesh is equal to blue, Orissa is equal to green. Varieties of CSPs. Discrete variables. Finite domains. Size D implies O of D to the power n. Complete assignments. Example: Boolean CSPs. Boolean satisfiability. NP completes. Infinite domains. Integers, strings, etc. Example: Job scheduling. Variables are start or end days for each job. Need a constrained language. Example: start job 1 plus 5 lesser or equal to start job 3. Infinitely many solutions. Linear constraints. Solvable. Non-linear. No general algorithm. Continuous variables. Example: building an airline schedule or class schedule. Linear constraints solvable in polynomial time by LP methods. Unary constraints involve a single variable. MP is not equal to green. Binary constraints involve pairs of variables. Madhya Pradesh is not equal to Gujarat. Higher order constraints involve 3 or more variables. Professors A, B, and C cannot be on a committee together. Can always be represented by multiple binary constraints. Preference. Soft constraints. Example: red is better than green often can be represented by a cost for each variable assignment. Combination of optimization with CSPs. Generate and test. GT. Very simple strategy. Just proceed with your assumption. Algorithm. Generate a possible solution. Test to see if this is actually a solution. Quit if a solution has been found. Otherwise, return to step 1. Example: N is equal to 4 queens puzzle. One possible solution is to systematically try every placement of queens until we find a solution. This process is known as generate and test. Disadvantages of generate and test. GT. It is not much efficient, for it generates many wrong assignments of values to variables which are totally overthrown in the testing phase. Leaving conflicted instantiations generators generates other assignments independently of the conflict. GT approach needs to be supported by backtracking approach for better efficiency. Traveling salesman problem. TSP. Input: graph V, E. Problem: find shortest path via all nodes and returning to start node. Input: graph VE. Output: path P1, P2, up to Pn, Pn plus 1. Solution: A, B, C, F, H, E, D, G, A. Length 22. Heuristic search techniques. What is heuristic search? Heuristic search, otherwise known as informed search or intelligent search, uses information of the problem to guide the search. Typically, though it guesses the distance to a goal state and therefore efficient, the search may not be always possible. Since heuristics are rules of thumb, they do not guarantee for a solution to a problem. In spite of being a weak technique, Heuristic search can be effective if applied correctly. They require domain-specific information. Characteristics of heuristic search. Heuristics are knowledge about domain, which helps search and reasoning in its domain. Heuristic search incorporates domain knowledge to improve efficiency over blind search. Heuristic is a function that returns value as estimated merit of state, with respect to goal if it is applied to a state. Heuristic evaluation function estimates likelihood of given state leading to a goal state. Heuristic search function estimates cost from current state to goal by having the notion that function is efficient. Example of heuristic search: 8 puzzle. State space: configuration of 8 tiles on the board. State initial: any configuration. Goal: tiles in a specific order. Solution: optimal sequence of operators. Action: blank moves. Condition: the move is within the board. Directions: left, right, up, down. Problem: which 8 puzzle move is best? What heuristic can decide? Which move is best? Actions: 3 possible moves: left, up, right.
Application of the heuristic search.
It falls in 3 different approaches. Count correct position of each tile. Compare to goal state. Count incorrect position of each tile. Compare to goal state. Count how far away each tile is from its correct position. First approach. Count correct position of each tile. Compare to goal state. Higher the number, the better it is. Easy to compute. Probably the simplest possible heuristic. Second approach. Count incorrect position of each tile. Compare to goal state. Lower the number, the better it is. The best move is where lowest number returned by heuristic. Third approach. Count how far away each tile is from its correct position. Sum up this count for all the tiles. The best move is where lowest number returned by heuristic. Heuristic search algorithm. Types: generate and test. Hill climbing. Simple hill climbing. Steepest ascent hill climbing. Simulated annealing. Best first search. OR graph. A star algorithm. Agendas. Problem reduction. And OR graph. AO star algorithm. Constraint satisfaction. Mean end analysis. Hill climbing. Generate and test plus direction to move. Heuristic function to estimate how intimacy between the given state and the goal state. Extending the current path with the successor node is closer to the solution rather than the end of the current path. If our goal is to get to the top of a hill, always takes a long stride step that leads you up. Simple hill climbing. Take any upward step. Steepest ascent hill climbing. Consider all possible steps and take the one that goes up the most. Local maxima. Considering peaks aren't the highest point in the space. Plateaus. A broad flat region gives the search algorithm no direction. Random walk. It is a large space. Ridges. Though it is flat like a plateau, it has drop-offs to the sides. Leading the steps towards the north, east, south and west may go down, but a step towards the northwest may go up. Simple hill climbing. Use heuristic to move states only when they are better than the current state. Always move to better state when there is a possibility. The process ends up when all operators have been applied and none of the resulting states are better than the existing one. Algorithm. Evaluate the initial state. Loop until a solution is found or there are no new operators left to be applied. Select, apply a new operator. Evaluate the new state. Goal implies quit. Better than current state implies new current state. Simple hill climbing. Example. TSP. Define state space as the set of all possible tours. Operators exchange the position of adjacent cities within the current tour. Heuristic function is the length of a tour. Steepest ascent hill climbing. The best possible state can be moved than the first better state. It is one move away. It does not matter about the order of operators. Not only climbing to a better state, but also climbing up the steepest slope. Algorithm. Evaluate the initial state. Loop until a solution is found or a complete iteration produces no change to current state. Successor is equal to a state that any possible successor of the current state will be better than the successor, the worst state. For each operator that applies to the current state, evaluate the new state. Goal implies quit. Better than successor implies set successor to this state. Successor is better than the current state, which implies set the current state to successor. Hill climbing. Disadvantages. Local maximum. A state that is better than all of its neighbors but not better than some other states which are far away. Plateau. All neighboring states have the same value in the flat area of search space. Means-ends analysis. It centers on the deduction of difference between current and goal states. Once such a difference is isolated, reduction of the difference must be found. That reduction has been executed by an operator. The action performed on the current state produces a new state. The process is recursively applied not only to this new state but also the goal state. It is quite possible that chosen operator cannot be applied to the current state immediately. Means-ends analysis. Example. Problem for household robo. Moving desk with two things on it from one room to another. Location is the main difference between start and goal states. Choose push and carry. Move desk with two things on it to new room. Carry. Preconditions cannot be met. Push. 4 preconditions. Walk to object. Clear desk using pick up and place. After push objects not on desk, must walk to collect them and put on table using pick up and carry. Problem reduction search. It involves reducing a problem from an entity to subproblems. Solutions of subproblems can be combined to form a solution to the hard problem. Recursive program. If the given problem is a primitive subproblem, one that can be solved by a known technique, surrender the solution to the expert. Otherwise, try breaking the given problem into sets of simpler problems and call the program recursively to try to solve the subproblems. After a set of subproblems is found, all the subproblems can be solved easily. Combine the subproblem solutions in an appropriate way to form the solution to the current hard problem. Problem reduction representation. The given problem is narrowed down to a set of simpler subproblems. In turn, those solutions enable the original problem to be solved. This reduction is applied recursively until primitive subproblems are at once reached the position of immediately solvable. The resulting structure is called an AND/OR graph. AND node. Solution of the main problem depends on the solution of the subproblems. An arc is drawn across branches of an AND node. OR node. Solution of any subproblem will solve the main problem. A state space search graph consists entirely of OR nodes. A successful terminal node is a solvable node. If a non-terminal OR node has any solved successors, it is also a solvable node. If all the successors of a non-terminal AND node are solved, it is a solved node. The problem is solved if the start node is solved. A solution graph is a subgraph of solved nodes that demonstrates that the start node is solved. Example for AND/OR graph is given here.
Conclusion. In this chapter, we have covered the following in detail.
Introduction and characteristics of weak methods. Heuristic search techniques. Generate and test. Hill climbing. Branch and bound technique. Best first search and A* algorithm. Problem reduction. AND/OR graphs. AO* algorithm. Constraint satisfaction problems. Means ends analysis.